Good evening, sir.
Good evening. We will start soon. Am I audible?
Yes, sir.
Okay, fine. So today we'll discuss blackbody radiation. Okay. So what is blackbody? Blackbody is an object which absorbs all the radiation imposed on it. Okay. So we'll start with Planck's law of blackbody radiation. We know that energy of a photon is equal to this E equal to h nu, right? Here h is the Planck's constant and nu is the frequency. Now this nu is equal to c by lambda. Here c is the speed of light and lambda is the wavelength. I think all of you know about special relativity. So
Yes, sir.
so you know this equation, right?
Yeah.
Okay, fine. So this is the energy of a free particle which is moving with some relativistic speed. Now what do I mean by relativistic speed? The speed of the particle by the speed of light is comparable to 1. Okay, so this is called relativistic particle. Now can anyone tell me what is the this mass is called m0 is called rest mass of photon. Here we are considering the energy of photon. Okay, so what is the rest mass of a photon?
0.
Right, it is 0. So the rest mass of a photon is 0. So we have E equal to pc, okay, for a photon. So we have E equal to pc equal to h nu. So nu equal to pc by h, or lambda equal to c by nu. Now put this the value of nu here, then we'll get h by p.
H by P.
Right. So lambda equal to h by p, or p equal to h by lambda. Now let's talk about the Planck's distribution we're talking. This is not actually Planck's law, this is about blackbody radiation. So now I will talk about Planck's distribution. Okay, what is this? This is, let's say this is equal to some dE, okay, some amount of energy. Okay, now what is this? This epsilon is equal to pc. This is for a photon. Okay, the epsilon I mean the energy is equal to pc. And what is ne? in epsilon, this is equal to this.
1 upon E h nu by kt minus 1.
Right.
Yeah.
Why is there minus sign? Because the photon is a boson. Okay.
Yeah.
I have
Both and
discussed right. I have discussed in the previous class that the number occupation number for a boson with energy epsilon is equal to this. Okay, and photon is a boson, so it will be like this. And this factor you all know about, right? Because you see, you have seen before, uh, when we are calculating this, it was like this. Okay, right? So this is this factor, this d3p dq, sorry, d3q by h cube. Here p is the momentum and q is the coordinate. Okay, now we'll integrate this equation over the entire space. Then what will we get? This is a free particle, so there is no space coordinate dependence here. I mean x y z dependence in epsilon or in epsilon. Then we'll just integrate this term. Okay, so d3q equal to v. This v is the volume. So if we integrate it and write it dE, then it will be v. And what is this d3p? This is equal to 4 pi p square dp,
Equal.
right? And what is epsilon? Epsilon is equal to bp into c here. And there is this factor here, pc by kbt minus 1. Okay, now we all know about the about that light is a electromagnetic light is an electromagnetic wave, right? And
Yes, sir.
it is a transverse wave. So there are two possible transverse direction, right? One is called longitudinal direction, and there are two possible transverse directions. So for that we need to multiply it with 2 factor. Okay, we'll multiply it with 2 here, 2 into this. So if you simplify it properly, then you will get 4 pi 8 pi v p square dp by, and there's some noise. If you have any question you can ask, otherwise okay. But we have discussed before that E equal to PC equal to h nu. Nu is the frequency. So this dE can also be written as, here I will replace this P by this h nu by C. Okay, so we'll get this thing. Now this dE I will call it V times du. Here du means it is like energy density, right? Because we are dividing it with V. Okay, so du equal to 8 pi nu square d nu by c cube into h nu by to the power h nu by kbt minus 1. Okay, this is called the Planck's law, or this du you can also write it like this. Okay, clear? Any question?
No, sir.
Now let's solve a problem.
So this you knew you have calculated. It is called density of states per unit volume.
Right.
Okay.
Who was asking this question?
Rakesh.
Okay.
My name is Rakesh.
Oh, okay. Actually, this is not the density of state. This is actually the energy density per unit volume, right?
This is the energy. Yeah, energy density
Energy
per unit
density
volume.
actually
Yeah. So
multiplied
if
with
I
energy,
want to,
right?
yeah, but
It's
if I
actually
doing with this only dqp and dqq by hq,
that
like in
that will be
the
density of
states,
state,
then it
right?
becomes the density of states per unit volume.
Right, right, right.
Yeah. Okay. Yeah. Thank you.
Hello everyone. In this video, I shall discuss question number 55 of GATE Physics 2020. This is a numerical answer type question. The Planck's energy density distribution is given by U equal to h cross omega cube by pi square c cube into e to the power h cross omega by kbt minus 1. At long wavelengths, the energy density of photons in thermal equilibrium with a cavity at temperature T varies as T to the power alpha. We need to find out the value of alpha. Let's solve this question. Here, the angular frequency omega is given by 2 pi into nu, where nu is the frequency. Nu is given by c by lambda, where lambda is the wavelength. So omega is equal to 2 pi c by lambda. Thus, at long wavelength, omega is small. This means at long wavelength we have h cross omega by kBt much smaller than 1. In this limit, we can write e to the power h cross omega by kBt as 1 plus h cross omega by kBt. In this question, we have u equal to h cross omega cube by pi square c cube into e to the power h cross omega by kBt minus 1. At long wavelength limit, we write e to the power h cross omega by kBt as 1 plus h cross omega by kBt. So we replace e to the power h cross omega by kBt by 1 plus h cross omega by kBt in the long wavelength limit. After some simplification, we get u equal to omega square kBt by pi square c cube. So we get u is proportional to t. Thus, alpha is equal to 1 in this question. So the correct value of alpha is 1.
Any question here? I think it's clear, right?
Yes, sir.
Okay. So we sorry, I need to share the screen. So here u was as a function of nu, okay, but in the question just we solved there u was as a function of omega. Now this omega is equal to this thing, okay. So how to get that equation from here? I am showing you that it will be, let's write it like this, okay. The total energy density should be independent of the choice of between omega and nu, okay. These two are actually equal, okay. So we have this d nu equal to d omega by 2 pi, okay. And sorry, and this should be this. And here also we need to replace this nu by omega by 2 pi, okay. So write omega by 2 pi in place of nu. and h nu equal to h omega by 2 pi. Now h by 2 pi we write it as h cross. So here will be h cross omega by kbt minus 1. Okay, so finally we get this equation. Oh, sorry, there was a 2 pi here from here. Okay, so this is the Planck's energy distribution function for omega, where omega is equal to 2 pi into nu. Okay, so we were talking about the energy density. Now let's calculate it properly. I mean, let's integrate it. And what is the range of this nu? What will be the limits of this integration? Let's consider it 0 to
0 to
infinity.
infinity.
Right. Now if you integrate it, then let's take h nu by kbt equal to x or y. Let's say y. Okay. So d nu is equal to kbt by h into dy. So u equal to 8 pi h by c cube into kbt by h whole to the power 4, right? Because there is a nu cube and d nu. Okay, nu equal to this thing and d nu equal to this, so we have to the power 4. Okay, so this term is independent of this y, so we'll take outside of this integral. Now see here, this is just an integral. It will give some number. Okay, it is independent of temperature. So what is the dependence of temperature here? U is proportional to T to the power 4, right? Clear or any question?
No, sir, no option.
Okay, I think it's clear, right? So we have U proportional to T to the power 4. This is called Stephen's law. Okay, now let's solve a simple question. Sorry.
Hello everyone. In this video, I shall discuss the solution of question number 8 of GATE Physics 2016. This is a numerical answer type question. The total power emitted by a spherical black body of radius r at a temperature T is P1. Let P2 be the total power emitted by another spherical black body of radius r by 2 kept at temperature 2T. We need to find out the ratio P1 by P2. Let's solve this question. In this question, the power emitted by spherical black body P1 is equal to U1 times the surface area of the sphere. Here, the surface area of the sphere is equal to 4 pi r square. So P1 equal to U1 into 4 pi r square. P2 is the total power emitted by another spherical black body of radius r by 2. So P2 equal to 4 pi U2 into r by 2 square. Thus P2 equal to 4 pi U2 r square by 4. So P1 by P2 equal to 4 U1 by U2. Here U1 and U2 are the energy radiated per unit area per unit time for the black bodies 1 and 2. From the Stefan's law, we know that U is proportional to T to the power 4. So U1 by U2 equal to T1 by T2 whole to the power 4. Here T1 by T2 is half. So U1 by U2 is equal to 1 by 16. We have found before that P1 by P2 is equal to 4 into U1 by U2. Replacing U1 by U2 by 1 over 16 in this expression, we get P1 by P2 is equal to 4 by 16 or 1 by 4. So P1 by P2 is equal to 1 by 4, which is equal to 0.25. So the correct answer of this question is 0.25.
Any question? If there is no question, then let's solve another problem.
Hello everyone. In this video, I shall discuss the solution of question number 43 of GATE Physics 2017. This is a numerical answer type question. The energy density and pressure of a photon gas are given by U equal to A T to the power 4 and P equal to U by 3, where T is the temperature and A is the radiation constant. The entropy per unit volume is given by alpha A T cube. We need to find out the value of alpha. Let's solve this question. From the laws of thermodynamics, we know that TdS equal to du plus P dV, where P is the pressure, dV is the change of volume, du is the change of internal energy, ds is the change of entropy, and T is the temperature. The total internal energy, capital U, is equal to the energy density small u into V. So du is equal to small u into dV. Similarly, entropy is equal to small s into V, where small s is the entropy per unit volume. So ds is equal to small s into dV, replacing du by small u into dV and ds by small s into dV. In this expression, we get T into small s into dV equal to small u into dV plus P into dV. This means T into small s equal to small u plus P. Thus, small s, or the entropy per unit volume, is equal to small u plus P by T. In this question, it has been given that P equal to small u by 3. Replacing P by small u by 3 in this expression, we get small s equal to u plus u by 3 by T. This means small s equal to 4 by 3 into u by T. Here small u equal to a t to the power 4. Replacing u by a t to the power 4 in this expression, we get the entropy per unit volume is equal to 4 by 3 a t cube. In this question, it has been given that the entropy per unit volume is equal to alpha into a into t cube. Thus, we get alpha equal to 4 by 3. In this question, we need to write the correct value of alpha up to 2 decimal places. So, alpha equal to 1.33. The correct value of alpha is 1.33.
Okay. Is there any question? Okay, if there is no question, let's continue our discussion now. Okay, we are discussing about Stephen's law. Now let's also discuss about Wien's displacement law. So I have shown this thing before. Now let's also write it in terms of lambda, the wavelength. Now lambda equal to c by nu, or nu equal to c by lambda. So d nu equal to minus c by lambda square d lambda. Am I audible? Hello?
Yes, sir.
Yes, sir.
Yeah.
Okay, fine. Now let's take a mod of this quantity, okay, modulus of this quantity. So if you take that, then you have c by lambda square into u of nu. Now here lambda equal to, sorry, nu equal to c by lambda. So replace that here, then I'll get this equation. So in terms of lambda, it is equal to 4 pi ac by lambda to the power 5 into 1 by e to the power ac by lambda kbt minus 1. Now let's assume that this quantity is much greater than 1. Okay. In this limit, we can replace this thing by this. Actually we are neglecting this 1 minus 1. Okay. So in that case it will be equal to Okay. Now let's find out the maximum of this thing. I mean the value of lambda for which this quantity is maximum. Okay. For that we need to differentiate it with respect to lambda. Okay, this is the condition of finding the maximum of this quantity u. So now we have to differentiate it. So if you differentiate the first term, then you will get this thing. Sorry. The whole thing at lambda equal to some lambda star equal to 0, and there is some 1 by lambda to the power 5. So this is the condition. So we have lambda star into t equal to AC by 5 kb. This is equal to a constant because this h is Planck's constant, c is the speed of light which is a constant, and kb is the Boltzmann constant. So this is constant. So we have lambda star into t equal to constant. Now what is this lambda star? Lambda star is the value of wavelength for which the energy density was maximum. Okay, so if the distributions are like this. Let's say these are like this. Here it is maximum, lambda 1, lambda 2, lambda 3, and the corresponding temperatures are T1, T2, T3. Here we have lambda 3 greater than lambda 2 greater than lambda 1. So but we have lambda t equal to constant. So T3 less than T2 less than T1. So this is a consequence of this Wien's displacement law. This is called Wien's displacement law. Okay, clear? Any question?
Yes, sir. Okay.
Okay, now let's solve another problem.
Hello everyone. In this video, I shall discuss the solution of question number 52 of GATE Physics 2018. This is a numerical answer type question. Two solid spheres A and B have same emissivity. The radius of A is 4 times the radius of B, and the temperature of A is twice the temperature of B. We need to find out the ratio of the rate of heat radiated from A to that from B. Let's solve this question. The rate of heat radiated from A, PA, is equal to UA times the surface area of the sphere A. So this is equal to 4 pi UA RA square, where RA is the radius of the sphere A and UA is the heat radiated per unit time per unit area. Similarly, the rate of heat radiated from B is equal to 4 pi UB RB square. Thus, PA by PB equal to UA by UB into RA by RB whole square. Here, the rate of heat radiated per unit area U is proportional to T to the power 4. So UA by UB equal to TA by TB whole to the power 4, where TA and TB are the temperatures of the sphere A and B respectively. Thus, in this question, we have PA by PB equal to TA by TB whole to the power 4 into RA by RB whole square. In this question, we have TA by TB equal to 2 and RA by RB equal to 4. Putting TA by TB equal to 2 and RA by RB equal to 4 in this expression, we get PA by PB equal to 2 to the power 4 into 4 square. After some simplification, we get PA by PB is equal to 256. So in this question, PA by PB is equal to 256. The correct answer is 256.
Any question?
No, sir.
So we are discussing about this Wien's displacement law. Now let's say you are given two distributions, okay, one at temperature T1 and the other at temperature T2. Now the energy density is maximum at temperature T1 at wavelength lambda 1, and at temperature T2 the energy density is maximum at lambda 2, wavelength lambda 2. Then we have lambda 1 into T1 equal to lambda 2 into T2. Now what is lambda? Lambda is equal to C by nu. So lambda 1 equal to C by nu 1. And lambda 2 equal to C by nu 2. So we get this expression. But we have seen before that this u as a function of nu, the frequency, you have this thing. Here also we replace this, actually we neglect this 1 term, okay. We are considering that this e to the power of this quantity is much greater than 1. Here also we do the same thing, the maximum of this thing, okay, we'll try to find out. from the first term we have this. So nu1 by T1 equal to nu2 by T2. We're getting the same thing, right? Before? Yes, we are getting the same thing. So nu1 by T1 equal to nu2 by T2. This is also important to remember. Let's stop here today. Next week we will discuss some problems on thermodynamics and statistical mechanics. We'll meet on next Saturday. I think it's 17th September from 6 p.m. Okay, let's stop here today.
Thank you,
Thank
sir.
you, sir.
Thanks everyone.